square by C Q D nu, right? This we derived.
Yes, sir. Yes,
So
sir.
this
Correct.
is the number. This is the number of standing waves. Now, as I told you earlier that I am very poor in remembering any formula, right? Very poor. If I am writing any formula correctly, that means I am writing it because of some concept. For example, what is the quantity on the LHS? What is the quantity? Yuras, what is the quantity?
Frequency.
Sir, energy density of spectral.
Frequency.
Sir, energy density of spectral
What is
lines.
the second term? What is the second term? I have written the second term. That is number of standing waves per unit volume, right?
Yes, sir.
Number of standing waves per unit volume. That means this quantity should have the dimension of number, any number, so that will be dimensionless. So number per unit volume, that means 1 by meter cube. That should be the unit of RHS. So you can easily calculate this. Nu is frequency, right? Frequency. And frequency is what? Frequency is 1 by time period. That means 1 by time. So you have frequency square and again frequency here. So frequency Q. So this will be, if I write only the unit here, then this will be for frequency, this will be second Q, right? Frequency is number of oscillations per second, right? So T each second, so 1 by second Q. And then you have in denominator, you have centimeter, this CQ. C is the speed of light in free space. That is speed. So speed is meter per second, right? And meter is length Q, meter Q is length Q, and then you have second Q, right? That is CQ. So second Q and second Q will get cancelled and we will be getting 1 by LQ. So that is 1 by meter Q. I should have written here meter Q instead of length actually, right? Okay, so this is meter Q. Is it clear, Yuras?
Yes, sir.
So that's the way I remember anything, right? See, the consistency of unit and dimension is a very, very useful tool for checking whether any formula is correct or not. I have seen students writing this particular number of a standing wave, something like this, say 8 pi nu q by c q d nu, or 8 pi nu by c square d nu. So I feel pity for those students that without understanding anything they are writing. This is not correct. This is also not correct. Okay, so we have derived the second term. Now the first term is average energy of an oscillator. So my expression is here now. Energy density, spectral energy density, of course, is equal to this average energy of an oscillator into number of standing waves per unit volume in the frequency range nu and nu plus d nu. Right? Now, average energy of an oscillator, this one. I hope that you must have studied one that is the that is known as equipartition of energy theorem. Equipartition of energy theorem. Have you studied in class 11th and 12th?
No, sir.
Yes, Yuvraj. Can you recall
No,
now?
sir.
If I write the formula here, then you will easily remember that yes, we have studied this. Equipartition of energy theorem states that the average energy of any entity which is at equilibrium with temperature T per degree of freedom is, I'm writing here, is half kT.
ये पढ़े है सर, ये फॉर्मूला पढ़े है।
तो यही तो है। This is the formula here, that is equipartition of energy theorem, that the energy of a system is equally partitioned, equally distributed among all its degrees of freedom. What is degree of freedom? Degree of freedom is the independent way, in which any entity can move, right? It can either move linearly or it can rotate. So if we have a particle which is moving in free space, then it will be having 3 degrees of freedom, because it can move either along x direction or y direction or z direction. Right. So the equipartition of energy theorem states that the average energy of an oscillator per degree of freedom is half kT. Okay. Now any oscillator will be having, this is per degree of freedom, right? This is average energy per degree of freedom. Per degree of freedom. Per degree of freedom. Right? Now an oscillator will be having 2 degrees of freedom. 2 degrees of freedom. How? One will be corresponding to potential energy and the other will be corresponding to kinetic energy. Any oscillator can have potential energy or kinetic energy. Right? So it will be having 2 degrees of freedom. So from here, I can write that the average energy of an oscillator, let us write that average energy as say epsilon bar, that is equal to 2 into 2 into half kT. Half kT is for per degree of freedom and it has 2 degrees of freedom. So it will be having energy kT, right? So this average energy of an oscillator is this, which I have derived. So I can write now this formula U nu as kT, that is the average energy of an oscillator, and then the number of standing waves per unit volume in the frequency range du and nu plus d nu. Okay, so this we have got. The mathematical expression we have got here for spectral energy density. Sorry, I didn't write in the correct format actually. Right? This left hand side is equal to U nu D nu, right? This is, you should have told, right? This is U nu D nu equal to, right? Whenever I am writing anything not correctly, then immediately you should point out. Don't be a mute spectator here. Okay, so this is equal to U nu is equal, U nu D nu is equal to KT. So this mathematical expression we have got. So what is our next? What is our next step? Yuvraj, can you recall what we have to do now?
So calculating the spectral energy density, since we got both of the terms.
So we have
Yes, sir.
calculated the spectral energy density. So what we should do now?
Sir, plotting the graph.
Right, very good. We should plot this and we should see whether we are going to get the experimental curve or not. Right? What is our experimental curve? Our experimental curve is this one. Our experimental curve for a particular temperature is this one. Right? Now, if I plot this formula here, what I will get? Right? This is nu here, and this is u nu d nu. So, can you predict here, Yuras, what type of curve we will get?
Yes. Sir, parabola of 3 degree.
Parabola. Very good.
Yes, sir.
Excellent. We will get parabola here, something like this. Because this is in the format of y equal to ax square. Right?
Sir, it's cube
ATK is the
actually.
mode. Yes?
Sir, d nu is also here. It's cube actually. D nu is also here.
No, d nu here. D nu is just associated with that frequency range. As I
So
told
it's a parabola.
that the instrument will measure the energy density in certain frequency range.
Yes, sir.
Right?
Got it.
Fine. So we will get this. So obviously, we are not getting this experimental curve. We are not getting this. What we are getting? So if I combine here both, then my experimental curve is this, but I am getting only this much portion, this one, right? This is the experimental portion here, and this is the parabolic curve here. So we have here u nu d nu, and this is nu. So what we conclude from this plot here? What is our conclusion? The conclusion is that this formula here, if I take this as equation 1, then this equation 1 satisfies the experimental curve, right? We should write here formula 1, formula 1 describes the experimental curve only at lower frequencies. Isn't it? For lower frequency, right? This is lower frequency, this much. But for higher frequencies, it doesn't satisfy, right? At higher frequencies, it doesn't satisfy. Higher frequency means lower wavelength. Lower wavelength. लोअर वेवलेंथ पर ये सेटिस्फाई नहीं करता है. लोअर वेवलेंथ मीन्स विच रीजन ऑफ इलेक्ट्रोमैग्नेटिक स्पेक्ट्रम? Which region of electromagnetic spectrum? Lower
Violet
wavelength?
blue.
Which
Sir,
region?
violet blue. Sir, violet region.
Ultraviolet, right? Ultraviolet region. So at in the region of ultraviolet, this formula 1 doesn't satisfy in the ultraviolet region. That's why this phenomenon is better known as ultraviolet catastrophe. Catastrophe. Catastrophe means a big disaster. catastrophe, a big disaster, right? And this formula one, this one, that means what I have written here, this one, this formula one, it is known as Rayleigh-Jeans formula. So two scientists' names are associated here. Rayleigh-Jeans formula. So what we have seen here that Rayleigh-Jeans tried to replicate the experimental curve, but they were successful only in the lower frequency region. That means higher wavelength region. Their formula couldn't satisfy the experimental curve at lower wavelength. That's why this incident is known as ultraviolet catastrophe. So very important question from your examination point of view, that derive Rayleigh-Jeans formula and explain ultraviolet catastrophe. Is it clear?
Yes, sir.
Is it clear? Madhuri, I don't think that you are understanding. Madhuri?
Yes, sir, it is clear.
Shashwat?
Yes, sir.
Suraj?
Yes, sir. समझ में से
See, I have uploaded the notes of previous class. You should go through the notes and take the help of your friends. Right? So very important question from your examination point of view, that derive Rayleigh-Jeans formula. That means we have to derive this equation 1 and you have to explain ultraviolet catastrophe. So I hope that somebody is having here a Beiser book, but some students are not having. So I can upload also, right? In fact, today I should upload. I'm going to upload this Beiser book after the class. Is it visible?
Yes, sir.
So this is page 71 of that Beiser book. It's an old edition book here, right? Black body radiation. You can see only the quantum theory of light can explain its origin, right? Just we have seen that Rayleigh-Jeans formula was not correct in explaining. So we have to move to quantum mechanics now to explain that experimental curve. So this is the birth of quantum mechanics, right? Let me move to, now you can see here, this I explained in the previous class that a hole in the wall of a hollow object is an excellent approximation of a black body. Can you recall? Shashwat? Oh, Shashwat was not there. Yuvraj, can you recall? We explained this.
Yes, sir.
Okay, now see
Thank
this
you.
ultraviolet catastrophe, right? So this ultraviolet catastrophe is explained here. Just see, right? Classical average energy per standing wave, half kT. This is 2.2, equation 2.2. Epsilon bar is equal to half kT. This is, we have assumed as average energy of an oscillator. So this is the Rayleigh-Jeans formula which I have written, equation 2.3. 8 pi kT by CQ nu square d nu. Right? Now this formula when plotted, so you can see here, it has been plotted. Graph is visible?
Yes, sir, it's visible.
So you can see here that we have an observed graph that we observe, and the other is Rayleigh-Jeans. So you can see that Rayleigh-Jeans formula satisfies the observed graph, the experimental graph, only at lower frequencies. Right? So now we have this. We have to derive this Planck's radiation formula, which is 2.4. This we have to derive now. So this was in 1900. In 1900, the German physicist Max Planck explained this ultraviolet catastrophe, and he got the correct expression, which when simulated just matched the experimental curve. Okay, and for this he was awarded the Nobel Prize. So we can have a brief introduction of Max Planck here, and you can see that he received the Nobel Prize in, here it is written, he received the Nobel Prize in 1918, and it is now considered to mark the start of modern physics. Modern physics means that quantum mechanics. Okay, so now our task is to derive Planck's radiation formula. So what is this Planck's radiation formula? Now, Planck's told here that, now first let us consider the drawback of that equipartition energy theorem. That means that epsilon bar is equal to kT, right? This is not correct. Max Planck told that this is not correct. The average energy of an oscillator cannot be like this. Why? Because this formula says that the average energy of an oscillator could be anything. Remember, K is universal constant, that is Boltzmann constant. And T is the absolute temperature. Now the temperature can be anything, right? Temperature can be anything. It can have any value, and depending on T, this average energy could take any value. That means epsilon bar values are continuous here. Are continuous, right? But Max Planck told that no, it's not like that, right? So there was two assumptions here. According to Max Planck, there were two assumptions, right? One assumption was that the average energy of an oscillator, the average energy of an oscillator here, that is equal to NH nu, right? Where N will be equal to 0, 1, 2, like that. Max Planck told that the energy of an oscillator can be only this. So you can see here that this is an index here, that epsilon 1 is equal to, sorry, epsilon 0 is equal to 0, epsilon 1 is equal to h nu, epsilon 2 is equal to 2h nu, epsilon 3 is equal to 3h nu. That means an oscillator can take only these values. It cannot take, say, 1.2h nu or 2.7h nu. No, it cannot have continuous values. It can have only certain values. What does it mean? That energy of an oscillator, epsilon, is quantized. Quantized. That means it can have only certain values. That's the meaning of quantized. The energy of an oscillator is quantized. It cannot have continuous values. Right? So you can imagine here that there are energy levels of for these oscillators, just like the energy levels of hydrogen atom. Okay, so this is the zeroth level and energy is 0. So I am writing here n, and then I am writing here epsilon n, right? So for n equal to 0, epsilon n is 0. For n equal to 1, epsilon n is equal to h nu. For n equal to 2, epsilon n is equal to 2h nu. Just I'm writing these things here, right? For n equal to 3, this is equal to 3h nu, and so on. It's like that. So these are the energy levels of oscillator, right? And the second assumption of Max Planck was that when an oscillator goes from higher state to lower state, then it emits radiation. And when it goes from lower state to higher state, then it absorbs radiation. And this emission and absorption of radiation, right, whether we take emission or absorption, this takes place, emission and absorption takes place in multiples of h nu only, in multiples of h nu. How? Suppose an oscillator is in the first energy level and it goes to zeroth one, then the difference of energy is h nu minus 0. So it will emit radiation of energy h nu. If it goes from say third level to zeroth level, then it will emit radiation of energy 3h nu. Similarly, when an oscillator goes from zeroth level to third level, then it will absorb radiation of energy 3h nu. It's similar to what we have you have studied in case of hydrogen atom. So whether it is clear, what are the two assumptions of Max Planck? Yes, Shashwat,
Yes, sir.
is it clear? The two assumptions of Max Planck?
यस सर. सर वो अगर मान लीजिए n मतलब इनफिनाइट तक है, अगर मान लीजिए वो n कुछ
n infinite तक है. Ideally n goes from 0 to infinity. Definitely, we will see that.
पर सर अगर मान लीजिए वो कुछ सर्टेन वैल्यू तक रखते तो क्या होता?
नहीं, certain value तक नहीं. Ideally, see, because always one should keep in mind that curve, this curve, the experimental curve. शाश्वत बोलो, ये कर्व कहां तक जा रहा है, किस फ्रीक्वेंसी तक जा रहा है?
वो तो नीचे मतलब जा रहा है, मतलब
हाँ, तो किस इधर फ्रीक्वेंसी इंक्रीजिंग फ्रॉम ओरिजिन, राइट?
यस सर.
तो कहां तक जा रहा है, किस वैल्यू तक फ्रीक्वेंसी जा रहा है?
वो तो इनफिनाइट तक भी जा सकता है.
इनफाइनाइट तक जा रहा है, वही तो हो रहा है, राइट?
यस सर.
So ideally nu goes to infinity. We are considering black body radiation. So theoretically, black body radiation, that means the emission radiated by a black body will have all possible values of frequency, starting from 0 to infinity. Ideally, theoretically. Is it making sense? Yuvraj?
Sir, yes, sir. If energy is not kT, if it is quantized as equal to
Right,
n,
it is quantized. See, the temperature, according to this partition of energy, average energy of an oscillator is kT. Now T could be anything, absolute temperature could be anything. It can be say 499.97. It can be having 532.57. Could be anything. That means energy could be anything. But Max Planck told that no, the energy of an oscillator could not be anything. It can have only certain discrete values. And those values are 0, h nu, 2h nu, 3h nu, 4h nu, 5h nu, like that. Right, but Shashwat asked here a very good question that if the energy becomes infinite, then what? So theoretically, energy can be infinite, definitely, because we have seen that in the experimental curve. If we have a black body, right, then it can emit radiation of any possible frequency. What about other students? Madhuri, is it clear?
Yes, sir.
Suraj, Suraj, Shrestha,
Uh, yes, sir.
Risha?
Yes, sir.
So again, at a question from your examination point of view, that what are the assumptions of Max Planck? So we have to write these two. That the energy of an oscillator is given by this, and the second one is that an oscillator emits energy when it goes from higher state to lower state, and it absorbs energy when it goes from lower state to higher state. And this emission or absorption of energy takes place in multiples of h nu only, right? Must be written in the book also.
Will you
Let me
repeat
see.
the second postulate?
Uh, yes, see here. 2.5 oscillator energy, right? So this is, read this one from here. It says that the oscillators in the cavity walls could not have a continuous distribution of possible energy epsilon, but must have only the specific energies given by this. And this one here, that an oscillator emits radiation of frequency nu when it drops from one energy state to the next lower one, and it jumps to the next higher state when it absorbs radiation of frequency nu. And each discrete bundle of energy h nu is called a quantum. Its plural is quanta, from the Latin word for how much. Quantum means how much. So this is page number 75 of Weiser book. So there are two assumptions. One, what will be the possible energies? And the second, how the energy will be absorbed or it will be emitted. Fine. So I will upload this. I will upload this. I will have to see what's the size actually of this file. Right? It is 32 MB, I think. 31 MB. So it can be uploaded. No problem. So is it okay now?
Yes, sir.
Now the next question is, we have got the energy of an oscillator, right? But there are so many oscillators here, right? Let me save this right now. My question is to find the average energy of an oscillator, right? Now we have several oscillators here. Once again, the same energy levels. These are the energy levels. Right? Now we can have several oscillators inside that black body, right? We can have oscillators in the zeroth energy level. So suppose these are the oscillators here, right? For circle represents the oscillator. We can have two oscillators in the zeroth energy level. We can have, say, one oscillator in the first energy level. We can have, say, five oscillators in the second one. We can have, say, three in the third one. We can have, say, seven in the fourth one. like that. So the black body will have so many oscillators. So the problem is how to find the average energy of an oscillator. Right? Average energy of an oscillator. Now, Yuvraj, you should tell here, right? Where my mouse pointer is?
Sir, at n equal to 3.
N equal to 3. So this is oscillator, one oscillator in the third energy level.
Yes, sir, there are 3 oscillators in the third
3,
energy level.
right. So what will be the energy of each oscillator in this level? What is the energy of each
Sir,
oscillator
3
in
h
this
nu by
level?
3. 3
No,
h nu by 3.
3h nu. Every here the energy of an oscillator in the third energy level is 3h nu, right?
Yes, sir.
Right. So what will be the total energy of these 3 oscillators?
Sir, 9 h nu.
9h nu. So what will be the average energy of these oscillators?
Sir, 3 h nu.
9, 3h nu, right? So that's the way. Our question is now that I should find all the oscillators in the black body, isn't it? What will be the average energy here? For this figure, what will be the average energy? How many oscillators are in the fourth energy level?
7.
Sir, 7.
7 हैं. तो टोटल एनर्जी कितनी हो जाएगी? 7 into 4h nu, right?
Yes, sir. Yes, sir.
What will be the total energy of the oscillators in third energy level? थर्ड में 3 है तो 3 into 3h nu हो जाएगा,
Yes, sir.
राइट. सेकेंड में 5 है तो 5 into 2h nu हो जाएगा, राइट. पहले में
Yes, sir.
1 है तो 1 into h nu हो जाएगा. जीरोथ में 2 है तो 2 into 0, राइट. और टोटल कितने कितने ऑसिलेटर्स हैं? 7, 3, 10, 5, 15, 1, 16 और 2, 18. तो ये एवरेज एनर्जी हो गया ना इस फिगर के लिए. Madhuri,
Yes, sir.
are you understanding?
Yes, sir.
So the question is how to find the number of oscillators in different energy levels. अगर मुझे ये पता चल जाए 7, 3, 5, 1 ये सब मुझे पता चल जाए कि कितने कितने हैं तब तो बहुत आसान हो गया मेरे लिए एवरेज एनर्जी ऑसिलेटर निकालने का, राइट. तो इसके लिए हम लोग जाते हैं पीछे में, राइट. And we have one formula here. Unfortunately, we are not supposed to study this. That is Maxwell-Boltzmann distribution function. Distribution function, which says that the number of oscillators in an energy level of epsilon is equal to a constant A 10 e to the power minus epsilon by kt.
ये फॉर्मूला देखे
What
थे
was our
आज
कहीं
समझ
देखे
में.
होंगे, डेफिनेटली कहीं ना कहीं जरूर देखे होंगे.
यस सर, आज समझ में आ रहा है.
एक्टिवेशन एनर्जी है.
So what what was our problem? Our problem was how to find the number of oscillators in different energy level, right? Fortunately, we have one expression here that says that the number of oscillators in an energy level epsilon is equal to this, where A is a constant, right? This is a constant which depends on the total number of oscillators. टोटल नंबर ऑफ ऑसिलेटर्स कितने हैं ब्लैक बॉडी में विच आर रेडिएटिंग, राइट? तो अब तो पता चल गया हम लोगों को कि what are the number of oscillators in a particular energy level, right? So what will be the average energy of an oscillator now? कैसे लिखेंगे? Yuvraj, can you tell?
Sir, HU into FE divided by number
Yes.
of oscillators.
What?
Sir, total energy divided by A E to the power minus E by KT.
टोटल एनर्जी कैसे लिखेंगे? Madhuri, can you tell?
F inverse A by A to the into E to the power minus E by KT.
Madhuri, can you tell? Madhuri,
Yes, sir.
can you tell? Just on this pattern we have to write. Suraj?
total oscillator into
फाइन, वो तो मालूम ही है, वो तो फॉर ऊपर वाले एक्सप्रेशन से तो पता चल ही रहा है, बट इन नोटेशन हाउ कैन वी राइट? लेट मी राइट, देन यू विल अंडरस्टैंड. Good that you people are understanding to some extent, right? It will be equal to total energy divided by total oscillators, right? तो टोटल के लिए सम कर देंगे, सम करेंगे या
Yes, sir.
इंटीग्रेशन लेंगे? युवराज, we will take summation or integration.
Sir, I think summation because energy is not continuous.
Very good. We are working not continuous values. We are working with discrete values. So what this will be? बस इसके पैटर्न पर मुझे लिखना है. 4h nu, 3h nu, 2h nu, h nu, 0. These are the energies. So energy of an oscillator and 7, 3, 5, 1, 2. These are the number of oscillators. So number of oscillators for a particular energy epsilon is this. And total oscillators will be this. I have just written this above expression in the form of notation.
Sir, what is E in the numerator?
Epsilon, that is not E, epsilon, epsilon. E-P-S-I-L-O-N, epsilon. This is
Yes, sir,
representing energy here. अभी तो बताया भाई epsilon. Epsilon is NH nu, energy of an oscillator.
And the number of oscillator is a function of that energy.
नहीं, F epsilon I have written here. F epsilon is this. Number of oscillators in an energy level epsilon. That is the distribution function. Maxwell-Boltzmann distribution function. Epsilon, F epsilon is the number of oscillators in an energy level epsilon. So let me write it explicitly. Good that you have asked this. So F epsilon here represents number of oscillators in an energy level of energy epsilon. अब क्लियर है?
Yes, sir.
तो अब मैं क्या कर रहा हूं? आई एम I am taking summation over all the energy levels. That means all the energies. So I will get number of oscillators, total number of oscillators. तो अब ये कितने के बराबर हो जाएगा? NH nu, epsilon is NH nu, that is the energy of an oscillator according to Planck's formula. And F epsilon is this. F epsilon is this. ऊपर में. So this will be equal to A, then e to the power minus epsilon, and epsilon is once again NH nu by kT. So this is numerator, and denominator is F epsilon, and F epsilon is A e to the power minus epsilon, and epsilon is NH nu, right, and by kT. ये clear है?
Yes, sir. Clear.
Clear है ना? Is it clear?
Yes, sir.
Yes, sir.
So now epsilon bar, that is the we write bar for average, right? Average energy will be equal to h nu. H nu, remember h nu is constant, which has nothing to do with summation, right? And summation is over which index? N, and n is from 0 to infinity,
0 to
right? So h nu, then n e to the power minus nh nu by kt, and this again divided by e to the power minus n h nu by kt. A will again come outside of summation because A is a constant. I have already written above that A is a constant. This is a constant which depends on the number of oscillators. So A will get cancelled. Right? So we have a very compact form, h nu, then n equal to 0 to infinity, then we have this n here, n here, n e to the power minus n alpha. Let us take, say, alpha equal to h nu by kt. H nu by kt is in the numerator as well as in the denominator. So n equal to 0 to infinity e to the power minus n alpha. So now it's only a mathematical treatment. We have to find the summation of numerator and denominator. कर सकते हो तुम लोग? Yuvraj, can you tell the numerator? This numerator is in the form of what?
sir summation.
कौन सा summation है ये? कौन सा summation series है ये? AP या GP या HP?
The geometric progression.
Geometric.
Sir, combination of geometric and arithmetic progression.
Very good, very good. This is combination of AP and GP, and the numerator and the denominator one.
So denominator is only geometric progression.
Only GP. Good. So I am writing only the final expression, right? Final summation. I hope that all of you can do it. ठीक है ना? अगर नहीं होगा तो मैं तो करूंगा ही, नेक्स्ट क्लास में डेफिनेटली मैं करूंगा. See, today I shifted my class from 9 to 9:30 because I was not ready with the lecture. And I thought that first I should carry out the summation. So I just carried out in the morning. Okay, so if I can do it, then you can also do it. Why not? So I'm just writing this. This will be equal to e to the power minus alpha 1 minus right? 1 minus e to the power minus alpha square. This will be numerator, and the denominator will be n equal to 0 to infinity e to the power minus alpha. That will be equal to 1 by 1 minus e to the power minus alpha. Right? This is your homework. I am writing here HW. माधुरी हो जाएगा ना ये?
Yes, sir.
ऋषभ?
Yes, sir.
चलो तो if I put these
Sir,
values
what we have
here,
to do? Can you explain the homework? I didn't
you
get
have
that.
to find the summation. You have to find that this is equal to this and this is equal to this.
Okay, sir.
So if I put these two values, then I will get epsilon bar h nu, right? So numerator is this e to the power minus alpha 1 minus e to the power minus alpha square, and denominator is this 1 by this. So denominator is this 1 by 1 minus e to the power minus alpha. So 1 minus e to the power minus alpha will cancel. So this will be equal to h nu e to the power minus alpha 1 minus e to the power minus alpha. Right? Now if I divide numerator and denominator by e minus alpha, then I will be getting h nu, and this will become e alpha minus 1. I have divided numerator and denominator by e to the power minus alpha. Is it clear?
Yes, sir. Clear.
Is it clear? So epsilon bar, that is average energy of an oscillator, is h nu divided by e alpha. And what alpha we had taken? Alpha was h nu by kt, right? So this becomes e to the power alpha, that is h nu by kt minus 1. So this is the average energy of an oscillator. That is the first term in our definition of spectral energy density. First term is average energy of an oscillator. That we have got. So what will be now a spectral energy density? That will be equal to average energy of an oscillator e to the power h nu by kt minus 1 into number of standing waves per unit volume in the frequency range nu and nu plus g nu. So what this will be in compact form, I'm writing this as 8 pi h by CQ, and frequency term I'm writing here. So nu q divided by e to the power h nu by kt minus 1 t nu. So this is the Planck's radiation formula, right? Just check here. Check here. Yes. Equation 2.6. Is it visible? Equation 2.6. Actual
Yes.
average energy per standing wave or per oscillator h nu divided by e to the power h nu by kt minus 1, which I derived. Right? This one. H nu divided by e to the power h nu by kt minus 1. And then we have that Planck's radiation formula. Probably it was written above. Yes, this one. Yes, Planck's radiation formula 2.4. 8 pi h by c q nu q d nu divided by e to the power h nu by kt minus 1. Right? And this will satisfy the experimental curve, right? It has been explained here. At lower frequencies and higher frequencies, you are getting this treatment on page number 75. Right? So again, homework for all of you that show that this Planck's radiation formula is consistent with, right? It's consistent with the experimental curve. So once again, homework. That means you have to show that this formula, when simulated, this formula, when simulated, will be this one. This I am leaving to all of you. Right? If you have understanding in understanding this, then you can refer to the page 75 of this book. ठीक है? Fine?
Yes, sir.
Let me save this also so that I can upload this for you people. So I'm going to upload the notes, the 3 paint files as well as the book. Fine. And in the meantime, you have this homework here. 2 homework I have given, the summation of the series, 2 series, one numerator and denominator, and the third one, this that show that Planck's radiation formula is consistent with the experimental curve. Okay, so I have tried